Good morning, one and all. There is no end to education. It is not that you read a book, pass an examination, and finish with education. The whole of life, from the moment you are born to the moment you die, is the process of learning. So now, let's learn something new from our eminent speaker of the session, Dr. Sarfaraz Masood. Welcome, sir. Now, I would like to give you a brief introduction about our speaker of the session. Dr. Sarfaraz Masood is working as an assistant professor, Department of Computer Engineering, Amia Millia Islamia, Central University, New Delhi. He is having specialization in applied intelligence, artificial neural networks, network weight initialization of sigmoidal feed forward neural networks, deep learning application of DL in the field of image processing and biomedical signal processing, evolutionary optimization technique. Now over to you, sir. Please take the charge. Now the mic is all yours.
Thank you. Thank you very much for this lovely introduction. Good morning, everyone. I hope I'm audible to one and all. There is some weather issue around, so maybe some network problem I might be facing. So please let me know time and again if there are any issues. Okay, so let me just share my screen once again. Sorry, this time I'll be doing it. Okay. Right. So is this visible?
Not yet, sir, but it will be maybe in a minute. Yes, sir. Your slide is properly visible to us.
Okay. Fine. So I welcome everyone who has joined this session. This is the session for introduction to computer vision with CNN using TensorFlow. So I'll be talking about CNNs, the convolutional neural networks, the buzzword these days as far as your problem handling is concerned with the vision problems, with image problems, and not just image, but now it's being applied to a whole set of applications within this. But I'll try to restrict myself to the computer vision section of application. So just to outline what I'm aiming to discuss in this session. Classical ANN learning framework. I will not delve too much into ANNs because I expect that is the fundamental thing that you must be knowing at present, but I'll still try and touch the basics about it. Then what obstacles do we have while we're dealing with computer vision? I mean, using a conventional shallow network or an artificial neural network. And then how does this convolutional neural network come into picture, and what advantage does it bring us along with the package? What are the various components that we need to understand if we are trying to implement a convolutional neural network? I would also love to talk about some convolutional arithmetics, like various calculations that happen within the convolutional network. So at least some portion of those calculations we'll try and discuss, which are relevant to our day-to-day applications of it. So some understanding about convolutional neural network we'll get after talking about these arithmetics. Similarly, how pooling happens and what those operations are and what the basic arithmetics are around it. Then we'll also try and understand how we can calculate the trainable parameters our model is actually having. So nowadays, not just the accuracy of the model, but also the computational complexity of the model is also becoming very important. Is my model too complex or still lightweight, even though being a deep model? So all those aspects we can handle. I mean, we can understand once we know the trainable parameter count. So I'll also try and discuss this with you, that how to calculate those numbers. I'll also try and discuss a basic fundamental CNN architecture, the LeNet. If time permits, I'll also go for AlexNet. Let's see. So it will be largely around CNNs, and finally, I'm going to touch the basic code structure for a CNN implementation using the TensorFlow API of Python. Okay, so artificial neural networks, I have strong belief that you must be having an idea about it. But still, let's just go through this concept. So these are I mean, this is actually a layered architecture where we have layers of computational elements called neurons. So these singular elements are actually neurons where computations are happening. So it's actually kind of a kind of a directional approach. So you can see the arrows, they're coming from the input layer, then going to the hidden layers, and then we have some output layers. And at each of these neurons, except the pink ones, the input layer, computations are happening. And those computations are, first the summation function is happening, and after the summation function, that is sum of all products of weights. So each input is going to the next neuron uh, with an effect of the weight of the link, the strength of the link. So you can see there is an edge between the pink node and the first yellow node, and between those on that connection there is a strength, that how much of that value will go to the next layer. So such way I have to sum up all the previous inputs, and that's the first component of a neuron, the summation function. And then I apply an activation function, a thresholding function, and
Hello.
also known as a squashing function. Yes.
Sorry to disturb you, sir, but PPT change नहीं हुई थी.
Okay, just a second. Let me share once again, please. Is the presentation visible? I'm on slide number 3,
Yes,
ANN
yes,
slide.
sir, it's visible now.
And is this moving now to the next slide? Can you
Yes,
see the
sir.
next slide?
Third, we can see the third slide.
डॉक्टर सरफराज इसको उसमें प्रेजेंटेशन मोड में कर लीजिए.
Okay, okay.
F5 से.
Yes, sir. Now is it moving to the next slide, sir?
हाँ, स्लाइड तो विजुअल है, प्रेजेंटेशन मोड में नहीं है.
सर मैं तो लेकिन प्रेजेंटेशन मोड में ही हूँ.
कोई बात
स्लाइड नहीं चेंज हो रही है.
कंटिन्यू करो, है ना.
Slides-
और बीच बीच में आपका वीडियो भी ऑन होना चाहिए क्योंकि ये रिकॉर्डिंग होगी.
बट सर मेरा वीडियो भी मैंने ऑन ही किया हुआ. आई हैव नॉट.
ओके.
Now
saying
it's
you can
visible,
share
sir.
your video.
We can see the fourth slide now.
Okay, okay, fine, fine. Sir, is my video also visible or not? Because I cannot
No, sir.
control that
No,
section
sir.
right now.
No, sir.
नॉट विजिबल.
Not visible. This
Are
button
you,
of video is unclickable at my end. I don't know
sir, you
why.
are using from browser?
Yes, I'm using through the browser.
Okay, through browser you can access either the webcam or the PPT.
Okay, okay. So only one of them is possible.
Yes, sir. Yes, sir.
Oh. Okay. So
Okay, sir.
should I go ahead?
Sure, sir.
यस सर.
Okay. Thank you. Thank you. Thank you very much. Fine. So we were discussing about this part. So the inputs coming to, I mean, all these processing nodes, they're having two functions, two operations being performed. One is the summation function and then the activation function. And once the activation function is applied, this a big sum of all products is actually squashed into a smaller element. The normal activation functions that we have are sigmoidal and tangent hyperbolic. The newer ones we have ReLU and leak ReLU and so on. So the problem that this layered architecture was good enough, and there were papers which said that this architecture having two hidden layers with sufficient amount of nodes can actually approximate any function, any continuous function can be easily approximated with single layer or two hidden layers at most. You can see the left part, the inputs. These had to be numerics only. These had to be numbers only. So let's say if I'm talking about an image problem, then I had to convert that image to numbers, some form, right? So it cannot directly work on those images. So some way I have to convert them. So either I have to perform some feature engineering, extract some features from it, or I have to give the pixels as it is to the system. So this input layer accepts inputs, the hidden layer processes the inputs, the output layer produces the final result of the network, and that I was expecting my model to give. Fundamentally, the network starts with random values of weights, and each layer is trying to adapt those weights. So that is the learning process. I'm not going to go much into that right now. So this was the classical ANN framework. There were images. I had to perform feature engineering, then give it to my classifier, and that classifier, upon training and learning, will give me results as this is class 1, class 2, or class 3. In my case, let's say this is class rose or dandelion or sunflower. So this feature engineering part was very important. So either I have to extract the feature, either I have to like do legless or some other way I'll talk about. So classical ANN framework requires feature engineering. It involves the following steps. Feature extraction. It is possible of extracting the set of possible features. So whatever possible features you feel, depending upon the domain of the problem. Image-based problems have different set of features to be extracted. Audio-based problems have different set of features to be extracted. Text-based problems
Dr.
have different
Sarfraz,
features.
again, slide is not changing.
I'm on slide number 4, so classical ANN framework. Is this visible or not?
No, sir.
This is,
No, sir.
no, this is ANN, third slide. Yes, yes,
Yes.
visible now.
Sir, please share it again.
Now I have exited the full screen mode. Now I am in the normal mode. Now the classical ANN framework is visible. This slide.
Yes, sir.
So I think in full screen mode it is not working.
Okay. Sir,
I
show us the fifth one. Yes, sir. Now it's visible.
changing now.
Yeah, yeah. Changing now.
Oh, okay. So some, I think unfortunately on my system it's not working on full screen. It
Yes, sir.
hangs maybe. Okay. So I'll try to zoom this part as much as possible. So I hope it's readable.
Yes, sir. It's readable.
Okay, fine. Thank you. So as I was saying that, the inputs that I'm having, if let's say they are from the image domain, they are images, then feature engineering has to be applied onto it. Then the outputs that I get from this feature engineering, which are actually a set of features, they are to be given to the classifier. So I have to extract features. I have to select even at times feature, because at times I can have numerous number of features, and out of those numerous number of features, which one to be selected, which best of them to be selected to give to be given to the classifier, was again a challenging task. So we used to apply feature reduction and all those feature selection techniques. So these two steps are imperative. So whatever domain you're talking about, you have to apply the corresponding one. So as I was saying, for images, I can have numerous number of features. I can apply some Gabor filter and get some features from it. I can apply Gaussian filters and get some features. I can apply some edge detection filters like Canny and Sobel. I can apply some pixel intensities, etc. So there are numerous number of those features. So out of those, first of all, I need to extract these, and then I need to select the best of the ones, and so on. So there are methods for that. Similarly, for audio, they can be, I may be extracting from my audio sample. I may be extracting pitch. I may be extracting amplitude. I may be extracting MFCC features, those MFCC coefficients actually. So then giving that to my system. So those are the ways of working with an ANN. So feature engineering is an imperative task. So if I'm talking about image related problems with ANN, so there are two ways of doing it. So as I just said, either I perform feature engineering and extract some specialized feature from my images, or I simply convert my two-dimensional image into a single one-dimensional vector of pixel values and then feed to my model. Now, what problem? This second approach seems quite simple. No need of any feature engineering. Simply give my pixel value. So if I have, let's say an 8 cross 8 image, so maybe 64 pixels I have. So give those 64 pixels in one dimension to the model, and ultimately you're giving the values of the pixel itself. So what better can it be? But there are problems in this approach. The number of trainable parameters will increase significantly with an increase in the image. So 8 cross 8 is 64, good enough. But if I move on to, let's say, 224 cross 224, some 50,000 input parameters they become. If I move on to, let's say, 1024 cross 1024, it even goes to something like 10 lakhs or around that value. So you can see, as the size of the image is increasing, the number of input parameters to my model are also actually increasing. So this way this approach doesn't look that favorable anymore. Second very important thing, that image is actually telling me the spatial uh, property of those components. Like for example, if I have a face over here in my image, let's say, then a forehead will be on the upper part, nose will be on the lower section of the, or the middle section of the image, the chin will be on even the lower section of the image, the nose and chin will be somewhat closer to each other. So there's spatial arrangement of these components. So if I'm trying to extract those features, then those features do have a relevance as far as the spatial arrangement is concerned. So if I convert my 2D image into a single one-dimensional vector, I'm simply losing out that very important information. So model is actually losing that spatial feature aspect of an image, the arrangement of the pixels in an image. Okay, so these will help me in what? In identifying objects more precisely. In fact, they can even help me in identifying the location of an object, or even rather a relation of particular object with other objects. So that is another disadvantage that I'm actually facing if I don't apply feature engineering and simply feed my input in the form of a pixel vector. If I do that, so here what CNN they help come for our help. So CNNs are actually are specialized networks. If I look at them broadly, then you can see from this diagram the feature engineering aspect has been removed, and instead I have the convolution neural network. So this network is actually doing the feature engineering for me. As simple as that. This initial section of my network, the convolutional part, is actually doing the classifier. I've just separated it from the fundamental section. So these convolutional networks, they have building blocks called kernels or filters actually, which are doing this miraculous thing for me. They are actually trying to extract those features which I was doing it manually. So these kernels help to automatically extract the relevant features from the input using the convolution operation. So this operation is actually applied at each of the layers, and by the help of this operation, I actually get to find out what features I was expecting. So one must give a thought to it. How does it know that which feature I was talking about? I listed numerous number of features for image. Those were only 4 or 5 features as I mentioned, but there are plethora of features. Let's say thousands of features I have. How does the system know that this is the very feature that should be used, or this is let's say there was a Gabor filter also, there was Gaussian filter also, there was canny edge detection filter, Sobel filter, so many filters were there. How does the system know that no, for this image you should apply Gabor, no, for this image you should apply Sobel, no, for this image you should apply a simple pixel intensity, maybe like that? How does the system know? So actually it adapts. We all know that the classical artificial neural networks, they adapt, they train what? They train the network strengths, those connection weights, they train that. But in the convolutional neural networks, these convolutional components, they actually also train, and they start with a random filter, they start with a random feature extractor, and then they try to adapt these feature extractors with each learning iteration. So you tell the system, this is my input and this is the output that I'm expecting. This is, let's say, a rose image, and this is the output I'm expecting, class 1 rose. This is another image for a dandelion, let's say, and this is the output I'm expecting, class 2 dandelion. So you are giving the system that this is the input I am having and this is the output I'm expecting. So system knows that what it is actually supposed to output. Now, starting from a random set of filters, it tries to match those aspects. Is it actually coming out to be that value that you were expecting? So with each step, with each iteration, it tries to adapt its filters. As simple as that. So extension, this is just an extension of those classical ANNs, but on a different aspect. So earlier we were only adapting the way which connection. Now in an abstract way, we are actually adapting these filters. So we start with a random filter, and then we adapt and adapt and adapt until a time the system actually knows, okay, for this image, this filter was far more important for you, something like that. So the process of convolving an image with these filters actually results in a feature map, feature map actually. So what happens? We give an image to the model, to the network, and then it applies a filter onto it. The output of that filter, once the filter is applied, that output is called actually a feature map. This is the map of features I've got when I've applied this filter. So any CNN will in a generic way will have 4 components very commonly in them. The convolution layers, you'll find some pooling layers, a flattening layer will also be there, and finally we'll have a fully connected dense layer. So we'll talk about each of them individually. Classically, if I show, this is the Leakin model. So this is how these look like. This is the input image that I'm giving. So on a small section, a filter is applied, and that the output of that filter is actually a feature map. So multiple times you'll apply these and you'll get those outputs. And once you have those feature maps, on those feature maps, you apply another operation called pooling operation. And once you've applied the pooling operation, you get another feature map. And then on that feature map, you can apply convolutions again. So one stack of convolutions and pooling, then another stack of convolution and pooling, then another stack of convolution and pooling, depending upon the level of feature that you want to find out. So the initial filters, actually, they're trying to find out the micro features in your image, maybe some edges, maybe some straight lines or some curved lines. Then the higher layers of convolution, they try to find out the macro features. So they'll try to add up those small features, and maybe they'll find out a face. Oh, sorry, maybe they'll find out the lip section. Maybe they'll find out the nose section. Maybe they'll find out the eyes section. And then the upper layers of the convolution network, the higher level layers of the convolution network, will actually try and merge these features to maybe find out one face, then the other face, and then the face, multiple faces also. So the initial layers of these of this stacking will try to find out the micro features, and then they will be aggregated to form the macro features. And finally, ultimately, we'll have on the extreme right hand side, we'll have some way of concluding that what does this set of features actually mean. So I'll conclude as an output. So as I said, convolutions are actually a series of convolution and pooling layers. Convolution operation extracts the features representation from the input data. So actually, we actually share these convolution filters over a spatial position. So I'll talk about that in details once I start doing example with you. And that what do I mean by sharing of filters? The shape and weights of the convolutional filter define the features to be extracted from the input data. So obviously, this will have an important role to play in what type of features the filter will give us. Usually, several filters of diverse shapes are used to ensure the diversity of the extracted features. So obviously, on my image, I'll apply. Okay, so I was telling that on a particular image, we'll apply several filters, and those two of different sizes and shapes, so that we can have a diversity of features that are being extracted. And once the convolution operation is over, then we follow it with a pooling operation that tries to extract most relevant of these convoluted features, that those which are of high, which seem to be of more importance, those are selected, and the rest are left out. I mean, you can also think about, because we're leaving out features, you can also think about that we're trying to downsize the feature map that we are getting from the previous layer. So convolution has given, let's say, an n by n feature map. Then this pooling will try to downsize it to, let's say, some m by n, where m is lesser than n. So by doing so, we are also helping out the network with the complexity part also. Okay, so if we talk about this convolution operation mathematically, then this is actually trying to understand that or it tries to represent actually how a function is modifying another function. So same is the case over here. You have an input image, you are applying a filter. You're trying to see how this filter actually affects this input image. What changes? So you will get an altogether different type of an input type of an output when you apply a filter onto an input. So a similar aspect is actually being evaluated here also. How this filter is actually modifying your input, or what it is actually extracting from your input. The main aim of convolution layer is to identify visual features in my images. These can be lines, these can be images, these can be some shapes, etc., etc., etc. The sliding application. Okay, so these kernels are actually slided over the image. So what I'm talking about sliding, I'll just show you in the next slide. So these filters are slided over the entire image, and once this has been applied to the entire image, this results actually in a feature map. The slide of the filter is also known as stride. This value is actually called the stride value, which decides the vertical and horizontal movement of the filter. So let me just show you this slide first. Can you see this image? And then you have a kernel. So this is the filter. The yellow color one is actually the filter, and this bigger image, your matrix actually is the input image. So now you can see this 3x3 filter is initially applied to the 3x3, the first 3x3 section. Okay, this is called convolution. So this is simple arithmetics. For example, look at the lower section example. The image is 60, 113, 56, 73, 120, 154, 131, 99, and 121. So this is the input. So these are the various values kept at the different pixel locations. So look what happens when I apply a filter over here. So the filter value is 0, -1, 0, -1, 5, -1, 0, minus. This is a random value, let's say. So how the operation is performing? So 60 into 0 plus 113 into -1. So corresponding locations are being multiplied, and this entire thing is being summed up. 56 into 0. So ultimately, once this entire operation is being applied, I'll get a value 266. So this 266 actually will be the output when filter is applied to one section of my image. So I've just taken out one section of my image. You can see this one section over here, the first non-zero part. You can see this to be location number 2,2, and this goes up till, let's say, I think 4,4. So this will result in output. So right now, initially, let me just get it to full screen. Can you see this GIF moving? Sir, can you see this GIF moving?
No, not moving.
Okay.
But slides are visible, and filter kernel are visible, no problems.
Okay.
But one thing, whenever I don't have any knowledge of deep learning because but I have done 15 or 18 year back filter on the images. So we used to take kernel center point at the beginning point, and there was a concept of padding and all. I don't know what is exactly here.
Yes. Same thing. These zeros are actually paddings over here.
Okay,
So I'm going to discuss those aspects. Don't worry, sir.
right, right.
Okay. So, but it's a bit unfortunate. I'm unable to zoom this because without starting slideshow, uh, I don't know why it's not coming out to be
Press
in the form of
F5.
a
See,
slideshow.
press F5 again.
No, I can see the slideshow at my screen,
Okay.
but
There.
can you see the full screen now, sir?
A screen is just like not full screen, but it is a full screen, but not in this presentation form. It is in the PPT form only.
Okay. Just give me a second, sir. Let me see if I can
Yeah,
get the full screen.
yeah. Take 1 minute, no problems.
Sir, this animation is visible only if you do the presentation, and for the presentation, if you share the whole screen, when you do the presentation, then it will be visible.
Okay,
You
okay,
should
fine.
share the whole screen.
Okay, okay, fine, fine. I'll do that. Thank you very much. Okay, now I've shared the whole screen. Is this visible in
Yes.
the?
Yes, sir.
Yes.
Now
Yes.
visible. Yes, sir.
Okay, thanks for the help. Actually, we are more
Yes. Yes.
using Google Meet rather than Teams, so this is a new
Right,
experience
sir.
for me as well. Okay,
Right, sir.
so I hope now this movement of filter is visible. So you can see this filter is actually sliding vertically and then horizontally on the entire image. This image has been padded with zeros around the borders. This is done so that the boundary pixels can also be can have a more role to play actually in deciding the features that are being extracted. Because अगर आप जो है वो if you are actually only selecting those if you're not padding it, then these boundary pixels will not have much role to play. They will not have central role to play. They will only have the side roles to play. So by doing those padding things, you will get more. They'll have more role to play actually in deciding the features that are being extracted. So you can see over here that with each passing of this filter, I get a value. I get a single value. So how many times it's being applied in the row part? 1, 2, we can 2, 3, 4, 5. So only 5 times being applied in the rows and 5 times being applied in the column. So I'm getting an output of 5 cross 5. This is the 5 cross 5 feature map I'm getting. So definitely it's not of the same size as my image right now. Even though it has been padded due to some restrictions, I'm getting a smaller size. So these are the features that it found out at initial level when this filter was applied. Okay. And I just given an example at the lower section that if I just take out the upper right part of this image and just try and write it over here that what operation is being applied, then this is the mathematics that is going around. So each element is actually being multiplied to the corresponding filter element, and then the sum is presented, and that sum is kept at, you can see 266 just came at the second row and second column. Because at the second row and second column, you can see that filter was selected. So whenever that filter is selected, its corresponding single value comes at the output feature map location. So how is it actually happening? So let's just take another example. Now this example goes to the participants also. This is the image I'm having. Okay, you have just seen the way it moves. This is a stride value 1. So at each iteration, the filter was shifted one cell to the right when talking about vertical movements. And then once the entire vertical movement was over, this was shifted one horizontal movement down. So now you've seen this movement. So now tell me, what will be the first output of this filter when it is applied to this image? So filter is 012 220 012, and the image you can see over here, it's actually a 5 cross 5 image. So obviously this filter will not be applied to the entire image at one go. It will be only applied to a small section or 3 cross 3 section of this image. So the first 3 cross 3 section is 332 001 and 312. Can the participants tell me in the chat window some way or the other that what will be the output?
The 12.
Yeah, absolutely right. So this is the output I'm getting. What will be the second output? When they apply, when this filter is shifted once. So now I'm talking about 321 013 112 122, this section of the image. If I apply this filter on this section of the image, what will be the output?
The 12.
Okay, I hope others are also writing in the chat window. So I'm getting 12 again. Next, it's now being shifted once more. It can be maximum shifted 3 times. So I'll be applying it to now 210 131 and 223. And once I apply this, I'll get the value as 17. So this is the way the filter is applied to one image. Now I'll move, no, because that's the maximum I could have gone in the vertical direction. Now I'll move to the horizontal direction. So now I've shifted it downwards. Now it's being applied to 001 312 200. The answer I'm getting is 10. Similarly, now the filter is moved to the next section, and you can see the output coming up is now 17 at this point. It's being applied again to the next section. I'm getting 19, and then shifted once more. I'm getting a value 9, and then 6, and then finally I'm getting this last value as 14. So on this image, I applied one filter, and I got a feature map of size 3x3. Now don't get confused. If the filter map is of 3x3, I'll get a feature map also of 3x3. That is not the case. We'll try and understand the arithmetic behind it. So last example was without padding. You can see no padding was applied. And now if I apply padding, so what will happen in this case, now the filter will have a different way altogether to move around. So a 3x3 filter, first of all, will work upon this. You can see 0, 0, 0, 0, 3, 3, 0, 0, 0. This upper left section of the image, and then this will be slided on. And now you can see the feature map that I'm getting is a bit bigger as compared to this one. So this was a 3x3 one. And over here, I'm getting a 5x5 feature map. So I'm getting a larger feature map. So you can see I'm extracting more features. A larger feature map means I'm extracting more features from my image. So padding helps me in extracting those. So now you can see why I was saying that there is a bigger role to play for the border pixels also. They can now contribute more features out of themselves. So the behavior of the convolution operation, I hope that is clear. How is it being applied? So a filter of some size n cross n, definitely smaller than the size of the image, will be applied and will be slided. I mean, it's a sliding operation actually. So it will be slided vertically as well as slided horizontally. Now we can have slidings of at least one. We can have slidings of two. We can have slidings of more than two also, 3 or 4. So stride values we can change. Just to give you an example, this is a kernel movement of 3x3 and 5x5 with a stride of, let's say, 2x2. So the first one you can see it's a 3. First one is a 2x. It's a 3x3 movement. So you can see the output coming out to be is this one, right? So a slide of 2 means it will be shifted at 2 points. So initially it was being applied to the first 3 elements, and then you can see the movement has been shifted to almost twice. It's not a shift of 1. It's actually a shift of 2. Next important point. Our images can be having multiple channels. We can have RGB images having 3 channels, one complete section for red, one complete section for green, and another section for the blue component. So our images can be multi-channels. So in that case, we'll have to apply a filter for each channel separately. Okay, so we'll have one filter for the R part, one filter for G part, and one filter for the blue part. For each RGB element, we'll have a separate filter to be applied. So we must be very much sure that what is the channel size of our image. Is it I mean, channel size is 1, channel size is 3, or whatever it is. So similarly, we have to apply the filters also. Those many number of filters we have to apply in that very case. Okay, so as I was discussing that how this output size is being calculated, let's talk about that. So in order to calculate the output size, this is the formula for it. So if let's say we are talking about square images and we're talking about square filters. However, we can also have, theoretically, we can also have non-square filters. Okay, but those are not very much popular, not very much applied, because the application of I mean their applications is quite very limited, and once because we're not very much aware that in which part of my image we have features. We don't know about that. If we would have known that at which part of the feature we have, let's say if my features are kept in vertical direction, so okay, I'll have longer I'll have filters which have longer number of column coverage and lesser number of row coverage. So maybe I can have a 2x4 filter. But if I know that much about my image, that's good enough. Otherwise, these square filters will also do similar thing for me. Okay, they'll be good enough to handle that aspect. So if I have, let's say, square images and square filters, the image size, let's say, is W. So W cross W image I have, and the kernel size, let's say I'm talking about K. So a K comma K or K cross K kernel I have. The stride value is, let's say, S, and the feature map, if I say the feature map size, the output size will be W minus K divided by S, and this value will be incremented by 1 plus 1. This is the formula without padding. If I apply padding, then this will be a 2 times p addition to the W, because you can see one row and one column is actually being added of zeros extra around each. I mean, if I talk about even just a row or column thing. So 2 into number of padding size plus the original width of my image will now become the factor with which I will find out the output feature map. So W plus 2p minus k. So the original formula remains same. It's W minus k divided by S plus 1. It's now W plus 2p minus k divided by S, because actually the dimension of my image actually has increased. Now it is W plus 2p size of my image. Okay. So if I apply this over here, what's the image size? It is 5 cross 5. Okay. What is the filter size? It is 3 cross 3. What is the sliding factor? It is 1. So 5 minus 3, the filter size. Okay. So 5 minus 3 is 2, right? 2 divided by stride value. 2 divided by 1 will give me 1. Will give me 2. Actually, 2 divided by 1 will give me 2. And then to this, I will add 1, which gives me 3. So a 3 cross 3 output feature map I'll get. That's the arithmetic going around. Okay. 5 cross 5, 3 cross 3 will give me 3 cross 3. Why? I've discussed about this part. So 5 minus 3 divided by 1, the stride value. And to this output, I'll simply add 1 to it. Now you can see over here the dimension of my image has changed because of padding. Now it is almost 7 cross 7. So 7 minus 3, which gives me 4. 4 divided by 1, because यहाँ पे अभी भी because sorry, here also the stride value is still 1. So 4 divided by 1 is 4 plus 1 gives me 5. So the output feature map will be of 5 cross 5. I hope this explanation is clear to everyone. Let me just take a question. Okay. So this is the number 128 cross 128 cross 3. The number of kernels I'm having, leave that part. That was not a part of the formula, but still, if the number of kernels I'm having is, let's say, 64. So actually, I'm applying 64 different filters, not just one filter. The theory says on one image you will apply multiple filters of different. Which are trying to find out different values. So I'm applying different 64 different types of filters of the same size, 3 cross 3. They're all of same size, 3 cross 3 filters, but almost 64 filters I'm applying. Okay. Stride value is 2 and padding is 1. Can you tell me the output feature map? The formula is W plus 2p minus k divided by S, and to this entire value you add 1 to it. If you're getting a decimal, try to apply the ceiling function to it, because I can't have a half of the cell explanation to it. So 128 minus 3, but we also have this 2p, 2 twice padding over here. The padding value is 1. Yeah. So what should it be? Are people giving answers, sir? I cannot see that window. I'm in the full screen mode. Okay, so I believe that this was the arithmetic that you all did. It's 128 plus 2 into 1, 2p, okay, minus 3. So 128 plus 2, it's 130, minus 3 is 127, and 127 divided by 2 will give me some value like 63 point something. This will be rounded off to 64, and then, 64, and then to 64, sorry, this should have been over here. Right, yeah. Should not be present wrong numbers here. And then to 64, I add 1, so I get 65. So you can see a 65 cross 65 output I'm going to get when I apply one filter. On one image, if I apply one filter of size 3 cross 3, then I'll get what? I'll get a a 65 cross 65 feature map from one filter. How many filters did I say? I said there are 64 filters. So I'll get into 64 outputs. So I'll get 64 different feature maps, each of size 65 cross 65. I hope this is clear. Okay. Next point, can you visualize, can you just think about it, how many number of parameters I'm having over here to train? Parameter is a number that I'm actually trying to adjust. Okay, it's a weight value that I'm trying to adjust. So as I said, these kernels I'm trying to predict. I don't know my kernels. I don't know what filter I'm trying to, what filter will give me the best value. So I'm actually adjusting my kernels. I'm actually adjusting my, you can say, yeah, I'm learning my kernels. So right now I have to learn a 3 cross 3 kernel. So that means 9 values will be there in the kernel that I'm going to adjust. Because if you look at this example, this 0, 1, 2, 2, 2, 0, 0, 1, 2 is a random value. God knows that maybe a 2, 1, 2 filter would have been a better one rather than a 0, 1, 2 filter. I don't know those values, so I'm trying to adjust. So in this filter, you can see there are 9 numbers which I'm going to predict, which I'm going to adapt actually, not predict, which I'm going to adapt, which I'm going to learn, which I'm going to train actually. So these 9 numbers I'm going to adjust. Okay. So for these 9 numbers, this is for one filter, 9 numbers for one filter. So how many total filters I have? 64. So 3 cross 3, 9, 9 cross 64. So that many number of filters for one channel of my image, because I said if there are 3 channels, I will have 3 set of features for, I mean, I'll be applying filters to all those 3, right? So ultimately the total value I'm getting is 64 cross 3 cross 3 cross 3. I'll have to check that number. Maybe I changed it. Just a second, please. Yeah, that is 1728. These are the number of trainable parameters which I have to adjust. 1728 parameters. Okay. So I am adjusting, I'm adapting. What I'm adapting right now? The filters, because the filters are unknown. I don't know them. So I'm adjusting them. So total filters at this layer of my network are 1728. So similarly, I can find out filters for the next layer. I can find out the filters for number of filters for the next layer. And then I can sum them up. Then the total number of weights which I'm adjusting in my model will come up. That will decide the complexity of my model. As I said initially, that most of our recent works, they also emphasize upon the model complexity, which can be described in terms of the number of trainable parameters which I have. So a reduced model, a model with lesser number of trainable parameters and a good amount of accuracy is considered to be a better one, because obviously it will be less power hungry. So I hope this arithmetic is also clear. So the way trainable parameters are calculated is different from the way the output feature map size is calculated. The output feature map size depends upon the input size. Okay. However, the number of trainable parameter size is not dependent upon the input size. It's simply dependent upon the filter size. How many filter? What is the filter size, and how many filters have I applied, and to how many channels they are being applied. Okay. So that's how I'll get the number. Okay, so next comes the pooling operation. So once I've applied convolution, I've converted my image to a set of feature maps. So 64 feature maps I have. So now to these feature maps, I will apply a pooling operation. So out of these feature maps, I'll try to find out the best of the values which should go forward, the best of the features which should go forward, and the rest one which can be left out. So by pooling, this can be a maximum pooling or an average pooling. These are the two most typical ones that are being applied. So these two filters I can have the pooling filter. There are also known as filters over here, because I'm taking out some values and I'm leaving out others. So it's actually a filter for me. So we gain robustness to the exact spatial location of the features. So where my best features reside, which are going to be helpful to make me the decision, This is actually what pooling is going to tell me, the best of the features. So if let's say this is the feature map I got from my previous layer. Now this is not the input image. This is the feature map I got from the convolution layer. One feature map I'm having. So let's say I apply a filter of 3x3, a pooling filter of 3x3, and that filter is, let's say, a maximum filter. So as the name suggests, pick out the maximum value from this 3x3 section of the image. The answer is 3. Okay. Next, slide it to the next 3 elements, and now again the answer is 3. Now slide it to the next one, pick up the maximum value, answer is 3. Slide it downwards to the horizontal location, again you get an answer as 3. You can again see the answer is coming out to be the max. So pick up the maximum value. Only one value was 3, rest all were 0. So I'm not talking about, so average will give me a different response. Maximum filter will give me a different response. So you can see these values coming out to be 3, 3, 3. Here you get the value as 2, which is the maximum. And finally, again, you get a value of 3. So this is the output of the pooling operation. It has reduced my feature map to a smaller feature map, which is actually having the maximum of the features, the maximized features, if I'm applying the max pooling operation. Now, one thing very important over here is that only the filter size was required. No number that 0, 1, 2, 2, 2, 1, 2, because over here, I know my operation. The operation is maximum of this section of my image. It does not require any numeric filter. Okay. So the operation is predefined. It's the maximum filter. So do I need to learn any numbers over here? No. The filter is not like the filter for a convolution operation. The convolution operation required a numeric filter. Over here, I have a functional filter. That maximum operation will be applied. I know that. I don't have to adjust that. I know my average filter. I know how average is calculated. So I don't need to adjust that. So because of this reason, pooling layers do not add to the trainable parameter quota of the model, because no filter is being learned. So to each, I mean, yes, some operation will be applied, but those filters will not be required. I mean, those numeric filters are not needed over here. But again, this conversion of my feature map to a smaller reduced feature map will happen, and this will not be a rocket science. Pretty easy. The way we have calculated the feature map for convolution layer, which is W minus K divided by S plus 1, something similar we'll have over here. Yeah, we don't have padding in this case. As simple as that. We don't require padding in the case of pooling. No need to add more numbers to it. This is already an extracted feature map from the previous layer. So output size will be W, where W is the standard, the input width, the width of the input feature map, and K is the filter size. So it's a square image and a square filter scenario. So W minus K divided by S plus 1. So if you look over here, it's a 5x5 feature map, and you can see the kernel size is 3x3. The darker blue section, you can see 3x3. So 5 minus 3 is 2, divided by 1 is 2 again, plus 1 will give me 3. So the output is coming out to be 3x3. Okay, so what will be 64x64x3? So it means I have an image of size 64x64 and of 3 channels, right? The max filter being applied is of 2x2, and the stride value is 2. Can you tell me the size of the feature map, output feature map? It'll be good if you all are calculating side by side. So it will be 64 minus 2, it will be 62. 62 divided by 2 will be 31, and 31 plus 2 will be 32. Yeah, very good. So 32 cross 32 cross 3, because I have a 3-channel situation. So for each channel parallelly, I'll be getting those 32 cross 32 size filters. So this is the output feature map I'll be having. And what about total number of trainable parameters? As I said, no addition to those trainable parameter size is going to be there. No addition to that part. So 0. So more, I mean, almost all the trainable parameters are coming from the convolution part, and no trainable parameters are coming from the pooling section. So as you can see over here, this is the fundamental linear architecture given by Leek and et al. In 1998. So this was considering a single channel image. So you can see the input images of 32 cross 32. And what the architecture said is the first we'll have 6 filters being applied of I think the size was 5 cross 5 maybe. Yeah, it was 5 cross 5. And then after that we'll have a subsampling layer or a pooling layer. Actually, after that we'll apply again 6 filters. So 6 at the rate means 6 filters being applied, and the size of each filter is actually I mean the size of the output feature map. Over here the output feature map size is being shown. The kernel size is not shown. I'll show you in a separate slide. So 6 at the rate 28 cross 28, that means I'll get 6 feature maps, and each feature map size will be of 28 cross 20. That means on this one single input of 32 cross 32, 6 different filters were applied. Not just one, not just two, 6 different filters were applied. So because all of them were random values, they were all talking about different aspects and different features to be extracted. So I'm getting that different set of those feature maps. Then after applying pooling, you can see pooling is simply reducing the size of these feature map. The count of feature map does not change. The count still remains 6. Okay. For each feature map, a reduction will happen. For each feature map, a reduction will happen. Because of 1, so we'll have the size is normally of 2, so it will be you will find a reduction in the size of this feature map. So subsampling layer or the pooling layer is actually reducing my feature map size from 28 cross 28 to a 14 cross 14. The number of filters, they remain the same. Then to these 6 filters, I'm converting them to actually to these 6 feature maps I'm getting at S2. I am applying actually 16 maps, and each of size 10. And the output size of each feature map that I'm getting later on is of size 10 cross 10. Then further, they have applied another pooling layer. And once this entire section is over, you can see they have converted their feature maps into singular components. So a flattening has happened. So this special operation called flattening, because actually you can see no matter how many times you apply this convolution and pooling, you will get you'll get an n cross n matrix actually. Okay. Because even the pooling layer was converting to an n cross n matrix. But my neural networks, if I talk about my neural network, the neural networks, they all require the inputs to be in one direction. I mean, they want the inputs to be in 2D. So I need to convert my 2D feature map into a 1D one-dimensional vector. Can be given input. So you can say those features converted to a single dimension. So that conversion of a 2D matrix to a 1D matrix is called flattening, which is very important. Without flattening, it will be difficult for the fully convolutional neural network to work upon. So this CNN architecture is a combination of 2 parts. The first part is the convolution pooling operation section, and the next part is actually the fully connected neural network, the classical ANNs that we used to apply. Maximum having 2 dense layers or 3 dense layers or 1 dense layer, or even for simple problems without even a dense layer. I mean, these layers are also called dense layers. Sorry, I didn't tell you that term. So these layers are also called dense layers because the connections over here are very dense. They are not sparse connections. They are very dense connections. If I have n nodes in layer 1, and I've got m nodes in layer 2, I'll have n cross m weights. I'll have n cross m connections. So these are very dense connections. Okay. So these dense layers, they are nothing but the conventional ANNs, and they will perform the classification. So you can see the first section of this architecture is extracting features, and the remaining section of this architecture is just trying to perform the same thing which the ANNs were doing for such a long time. Give me the features, I'll perform the classification. So the human intervention part has been removed. Now I don't need to do those feature extractions. Those feature extractions can be simply done by these convolution and pooling operations being applied initially on the image. So I'm randomly starting with some random feature being extracted, and then I try to correct myself. No, this feature is not good. I need something else. So I'll change my filter, and then I'll change it again. Then I'll change it until and unless I get a set of features which are actually giving me the same output or something very similar, which I was supposed to get. Okay. And the rest of the things are very much in sync with what how ANN used to train. So a same backpropagation based learning algorithm is good enough for them to train. Okay, this I would like to do with you all. Right. So you can see this is the linear architecture, and I'm over here. I have a table that is defining how many number of feature maps I'm having, and what kernel size I'm having, and the output of that or yeah the feature map size or the input image size is what. So this is being told over here. Can I calculate the weights and bias? Let's see. So image right now is having the size of 32 cross 32. Okay. And on this 32 cross 32, I apply a layer called convolution layer. And the size of this convolution filter is of 5 cross 5. And how many filters do I apply? I apply 6 filters. Okay. So let's see, do I get this number 28 cross 28? So 32 minus 5 will give me 27. 27 divided by 1 stride value will be 27 plus 1, as we are always doing it, plus 1 will give me 28. So this is right, 28 cross 28. This is how I should get. Next, on this 28 cross 28, I apply a pooling, average pooling. Okay. The size of this pooling filter will be of 2 cross 2. And the stride will be of 2. So 28 minus 2, because on this I'll apply, na? On this convolution output, I'll apply. So output of the convolution is 28 cross 28. So on 28, I'll apply a 2 cross 2 filter. So 28 minus 2 is 26. 26 divided by 2 will be 13. And 13 plus 1 will be 14. So a 14 cross 14 output I'll get from my pooling layer. Then it's saying after this pooling, I am again having a convolution layer, and this convolution layer will have a 5 cross 5 filter size. So on 14 cross 14, when I'll apply a 5 cross 5 filter with stride value 1, what should I get? 14 minus 1 is actually 9, and 9 divided by 1 will give me 9, plus 1 will be 10. So you can see this number is correct, 10 cross 10. So I hope you're also getting the same numbers I am calculating with you. On this convolution output of 10 cross 10, I'm applying again a 2 cross 2 filter. You can see the size again decreasing because the stride value is 2. Then to it, I'm again applying a convolution. So this is not a convolution. Actually, this is nothing but a flattening. So you can see this has been flattened. So on this output of 5 cross 5, I'm simply applying what? I'm applying a 5 cross 5 filter. So when you'll apply the same size filter on the entire image, okay, so what you will get? You will get single output. Na? 5 minus 5 will be 0, right? And 0 divided by 1 will be 0, plus 1 will get only 1. So you will get a 1 cross 1 filter. So how many filters you're actually applying? You're applying 120 of such filters. So this is nothing but you're simply flattening your previous layer's output. Okay. So I hope these numbers, you're also getting the same numbers. And after that, in this to this 120, you will have first layer of 84 nodes. FC layer means fully connected layer. So first layer of 84 nodes and the next layer of 10 nodes. And this C5 was a convolution operation of 120. So this was a flattened output. You can see this, the flat gray line. This is a flattened output. Yeah, this is better. So, sorry. So now let's just calculate the waits for it. Right. So the right 5 cross 5 into number of filters 6 into the feature maps that we had in the previous layer. How many feature maps we had in the previous layer? So it is 5 cross 5. That means 25 into how many filters I'll have? 6. So 25 into 6 is 150 and 150 into 1 because previous layer the input is the unit architecture. It's having only one. I mean, it's a single channel image. Next, bias. For each filter, for each entire filter, I'll have one bias. So the bias count is actually exactly equal to the number of filters that I'm applying. So 6 filters I'll apply over here. So a sum will be at this layer will be 156. Pooling does not contribute a 0. Now, what about convolution operation? At this layer, at this level, the kernel size you can see is 5 cross 5. So 5 cross 5 give me 25, and again 25 into how many filters are actually I'm getting is
Excuse me, sir.
in the previous one I was having.
Excuse me, sir.
6.
सर आपकी वॉइस बहुत ब्रेक हो रही है.
So yes.
सर आपकी वॉइस बहुत ब्रेक हो रही है.
Okay. Right. So I think this 000 was clear, or should I start from this 150? How did I get this 150? Till this part, my audio was clear or not?
Yes, sir.
Okay. So this is I'll just give it a brief view. So this is 5 cross 5 into number of filters I'm having. 5 cross 5 into 6, and then this into 1 will give me the total count. Okay. So next I'm having I mean the average pooling I'm having as all weights as 0, biases as 0, so no addition to the number of trainable parameters. And then this will be again 25 into this is now I'm having as 16. So 16 into 6. So it will be almost 600 I'm having. Okay. And then how many this will be? I'm having 16, so I'll have 616. Okay. And then again the pooling one will not have any contributions to be made. Then at this one I'll have a 5 cross 5 into 120, so this will be 25 into 120 will be somewhat about like 3000. Filter size this, and then this comes out to be 120 for each filter. I'll have so 3120. And then at this layer, I'll have how many for the fully connection? It will be 120 cross 84. So I'll apply this. So 120 cross 84. This will be 10080, and then 84 total. I'll have because I mean these are the number of nodes I have in the fully connected layer. So 84 I'll be simply adding to it. So this will be plus 84 will give me 10164. These many number of parameters I'll have in this layer, and then it will be simply 840 because 84 into 10 at the fully connection at the fully connected layer. It is simply a multiplication of the two number of nodes. So 84 and 10 will be 840. 120 into 84 is 10,080. So a simple addition, and 10 nodes over here. So it will be 850. You sum them up, you will get the total number of trainable parameters. Okay. Similarly, we can have it for the AlexNet. This architecture is somewhat, I mean, this is quite different from the previous one. But just to give you an idea about the way that we have calculating is fine or not. So over here you can see the AlexNet is typically meant for a 3 channel image. 227 cross 227 cross 3. So 3 channels I'm having, and to each channel I'm applying the filters. This is the architecture that the AlexNet has. So how many number of filters I'm having and what is the size of each filter is being mentioned. And if I have this, similarly, very similarly, I can calculate the trainable parameters over here. Okay. So this would help you in understanding how many number of parameters I'm actually getting. Now, one very important aspect to see over here. Can you see these numbers at the FC layers? They're so large. They're so very large. Okay, 37 lakhs, 16 lakh, 4 lakh features to be trained. But over here in the upper section, these numbers aren't that big. They're not that big, although the computations happening are quite high, but these parameters that I need to train, that I need to adjust. So because training time actually depends upon this largely, how many parameters I'm going to train, how many parameters I need to adjust. So you can see that these FC layers actually are computation intensive, but they're not highly intensive on the part of the trainable parameters. These trainable parameters are quite significantly less as compared to the number of trainable parameters that come from the FC layers. I cannot do away with FC layers because the fully connected layers or the dense layer, they are the classifier for me. So I cannot do away with them completely, but definitely this feature extraction part of my model has significantly reduced my parameters. Had I not been doing this, my manual intervention would have been quite high, and these numbers could have even gone up if I would have been using a traditional one. So just to give you an insight about it, that the FC layers still contribute more in terms of weights, the parameters to be trained, and the initial layers, they do not contribute that much on the trainable parameters part. They are quite less. Each layer to be compared is quite less as compared to the previous one. Okay, so now that we have had a theoretical idea about what CNNs are and what operations are being performed in them, and what all different layers do we have in them, can we club these things together to form a CNN model for, let's say, a very starting sample, let's say on the MNIST data set, which is the character data set actually used quite often to highlight the performance of or the working of the convolution neural networks. So in order to build any convolutional neural network, these 5 major points I have highlighted. So first of all, we'll need the data set. We'll have to load the data set, okay, which will require some pre-processing of the data set, some reshaping and some augmentations depending upon what type of problem you're working around. This component can be of variable operations, sub operations. Okay, and then finally, if it is not divided, if the data set that you're having is not divided already into training and testing sets, then you have to divide your data set into training and testing and validation. Normally, this is usually accepted to be 70, 15, and 15% if you are having training and validation and testing. But if you're only having train test, then 80-20 is a very, very acceptable proportion in which you can divide your entire data set. Followed by this, you have to build your sequential model. These CNNs are actually nothing but sequential models. Your entire set of nodes, your entire set of layers are actually kept in a sequence. So you add some convolution layers, you add some pooling layers, which are finally followed by a flattened layer, and then finally you have some dense layers. All the architectures that you talk about, they are having some combinations, some permutations and combinations of these, which are ultimately followed by this. Finally, they have to their all features have to be flattened into a set of features that it got from the image, and finally they are applied to the dense layer, to the classifier. They are given to the classifier, to the dense layer. Once the model has been built, we have to compile the model. That is, we have to define the network optimizer, which optimization algorithm we are using. Are we using the stochastic gradient descent, or are we using the adaptive momentum, the Adam algorithm, or the Nesterov momentum, the NADAM? I mean, there are multiple optimizers available with us for. I mean, when we are talking about TensorFlow API, which loss function we are using depends upon the kind of problem that we're handling. If it is a binary classification problem, that then we will normally have the binary cross entropy function. If you're having a multi-label scenario or a multi-class scenario, then we can have simply categorical cross entropy. We can have MSCs also. We can have other loss functions also. Then we also try to define what metric we are trying to optimize, what metric that we are trying to follow. It can be accuracy or something else. Then once we have compiled the model, that is, we have defined these parameters, we try to fit our model. We try to train our model. I coming from the MATLAB domain, we used to call it training the model. There was a train function over there, but in the Python counterpart, we have this function called fit. So we fit the model over here. So we define the training data. What will be the training data for a model? What will be the validation data for our model? What will be the network hyperparameter values? How many epochs? How many batch size? And then once we have set all these things, we try to train the model. So this is what fit function does. This is what compile function does. And this is what our building sequential model is talking about. And once we have trained our model, then this is nothing but the right time for us to evaluate the performance matrix. So we can have we can evaluate multiple performance matrix. If it's a classification problem, we can have performance matrix like precision, recall, accuracy, FN score. If it's a regression one, then we can have the coefficient of regression, the MSC, and other values we can talk about. So these four, 5 aspects are the very broad aspects within which I'll find most of my programs in as far as computer vision problems are concerned, and we're trying to build up a CNN for them. So this is the MNIST data set, just some random samples from it for you all to see. So you can see the 0 being written. These are handwritten images, or handwritten character images actually. So for loading the data set, depends upon the scenario. Are you loading the data set from the TensorFlow library, or you are having a separate data set maybe at your drive, or you're having the data set you're picking up data set from Kaggle or some competition website. So it depends upon. So this code will change on the aspect that you are having, what scenario you're using. Okay, what pre-processing you are applying will decide these codes. This is just a sample code that I'm showing you for the MNIST one. I'll show you this code on the collab also right now. Just give me a minute for that. So you can see I'm doing some reshaping of my images, and I'm defining the type of my my training and testing data. In the MNIST dataset, I already have the dataset divided into train and test. So X-train means the inputs for the training part, and the Y-train means the labels for the training data. X-test means the input for the testing data, and Y-test will mean the labels for the testing data. So simply by doing this command, I get this data pretty easily into this. This is a preloaded data set I get with the TensorFlow library. So once the reshaping or other pre-processing things are done, I try to build my model. Now, this is the important part that we need to see. Building the model, what we're doing, we simply first define the shape. What will be the input to my model? What's the shape it will have? And then you can see I'm simply adding a convolution layer. The function to it is model. Model I've defined as a sequential model. And then to it, add a convolution layer, as I just showed you over here, right? Convolution layer, then pooling layer, then convolution layer, then pooling layer. So I can have some combinations of it. So you can see I've added a convolution layer. These are the number of filters I'm saying it will have. This is the size of each filter. This is a stride value. Am I applying padding or not? Valid means I'm not applying padding. If I write same over here, if I write same, it means that the output size, the size of the feature map will be same as the size of the input image of the or the input to this layer. So same, it means you have to apply padding, and that much number of padding that the output comes out to be exactly of the same size as that was the input. But if I don't want padding to be applied, then a simple valid will be good enough for me. Sorry. Oh. Yeah, here it is. So padding by, this is the activation function I'm specifying in the convolution layer, because convolution layer ultimately applies activation also. So I'm applying the ReLU activation function. So this is because the first convolution operation I'm defining the shape. In the first convolution layer, you have to define the shape of its input actually. What shape it will get, what will be the dimension of the input that it will have. And then followed by this, I'm applying a max pool. You can see over here, I'm simply applying a max pool. So convolution operation, pooling operation, then again a convolution operation, then a pooling operation. And once this operation has been done, I simply apply the flatten layer. So this will convert my two-dimensional output of this max pool to a single one-dimensional vector. And this one-dimensional vector will be given to the, sorry, it will be given to this dense layer. And this dense layer is having how many? 100 nodes. So whatever output this will have, this will be multiplied with this 100. It will give me that much number of weights to be adjusted. Again, the activation function is being defined because these layers are actually performing operations. So I have to compress those outputs. So a ReLU function is being applied. And at the output layer, I'm having 10 nodes. Why 10 nodes? Because the MNIST dataset has actually 10 classes. So the last layer in your classification problem, the last layer of your model will have the same number of nodes as you have the number of classes in your dataset. So I'm having over here, let's say 10. So 10 is being applied. And then finally a softmax function. Normally at the output layer, we have a softmax function, which is slightly different from the it actually gives me the probabilities of the output, which are converted to finally a 0 or 1 on that node. And this last line is actually giving the summary of my model. So it will give me a printed summary, something like this. This is the way it will give me an output that to my model, I'm having a convolution layer. And the output of this convolution layer is 26, 26, 10. You can calculate. Now, I hope you are good enough to calculate those. So my input was 28, 28. Stride value was 1. And the filter size I've already given. So filter size was, let's say, I think 3 cross 3. So now these numbers can match up. You can calculate how these numbers are coming. So then max pooling was applied. Then convolution, a 2D layer was applied. Then max pooling again was applied, which was followed by a flatten layer. So you can see this 5 cross 5 cross 10. This was the output of the pooling, max pooling layer, 5 cross 5 cross 10. So 5 cross 5 is 25, 25 cross 10 is 250. So this was actually 10 feature maps I had, each of size 25 cross, each of size 5 cross 5. So these 25 feature, these 10 feature maps of 5 cross 5 have been converted to one single feature vector of 250 samples. And this has been fed to the dense layer of size 100, and then again a dense layer of 10.
Excuse me, sir.
Yes.
So your voice is breaking again.
Okay. Am I audible now?
Not breaking. It is okay. Normal.
It's okay. Now, sir.
Okay, fine. Thank you. Okay, so after the flatten, you can see I've applied 2 dense layers, and the final dense layer is actually giving me the outputs. The 10 classes that I've defined. So on one of the edges, I'll get a 1. On the rest of the edges, I should get a 0 if my classification is happening fine. For the MNIST dataset, I plotted some curves. So this is the loss plot, the error plot, and this is the accuracy plot. You can see these are good plots to be considered because the the blue part is actually the training loss, and the orange or slightly yellowish one is actually the validation loss or the test loss that I'm calculating parallelly with the model. So with each epoch, you can see that this is a downward curve, and the loss should look like this. And these both these validation and loss curves are quite close to each other, and they're not highly divergent, meaning my model is overfitting. I hope you all know this concept of overfitting. Overfitting is actually referred to a scenario when I'm having a very good training loss or a training accuracy, very good, but the test or the validation one is very poor. It somewhat hints me the fact that I'm actually, rather than learning, I'm mugging up those inputs. So I'm getting too specific to my inputs. So my the generality of my model is actually getting hampered. So for unknown data, I'm not doing good. But for the data which I'm being fed again, because what happens in training, I have multiple epochs, and the same data is being fed again and again and again in different epochs. Okay. So on the data which I'm seeing again and again, I'm having a good performance. But on the data which I've not seen, or which my model has not experienced so far, it isn't working that good. So that is a scenario of overfitting. So I can look at this curve and see that the they're pretty much close to each other, and they're going in the right direction. The accuracy is increasing, is an upward direction. The loss is a downward direction curve for me. So these are acceptable numbers, and they are pretty close to each other. However, in realistic problems, we can have very jittery kind of curves, but the direction of those curves hints us that are we going in the right direction or not. Then finally, we can also plot the confusion matrix, which can help us to visualize the performance of a model. So it's a very good visualization tool. So you can see 10 classes. So a 10 cross 10 vector, 10 cross 10 matrix, you can see. So these diagonal elements are actually the true positives. So the elements of class 0 were considered to be were actually predicted to be of class 0 with a very high performance. You can see these many number of almost you can see a greenish tone, so maybe 950 or 960 elements out of those 1050 were predicted well. So the class 1 elements were very accurately predicted, and so on. So very light blemishes we find on the either sides of the border. That means the model was doing very good. The class of that element that should have been predicted is actually very largely being predicted of being the same quantity. Okay, so now let me move on to the the collab part. So let's just see how this goes when I run this program on Google Colab. So Google Colab is a free kind of a platform for me for running for testing our deep learning programs on. I mean, they have the pre-installed libraries for us. They have the Keras, TensorFlow. They're all available over here, and I don't need to worry about the dependencies of the packages. So it's a very good tool for starting our learning on this. They are getting tighter and tighter day by day on the various aspects, like for how long can you use the GPU. I mean, they provide you a GPU also with a 12 GB of VRAM. They provide you enough RAM capacity as well. So, but that is not. I mean, that is free only to a certain extent. I mean, sometime or the other, you must have gone through this part. They have even launched another variant of their Collab version that's called Collab Pro, which is about like $10. You can have it for. I mean, you can have your sessions for a longer duration. So if you're really going to use Collab for your work, then I would recommend that you go for Collab Pro, because for 1 day extensive use of Google Collab, they will stop showing. They'll stop providing you GPU. They'll just start saying that your consumption has been quite high. And in their policy, they have also mentioned that you should not use GPU for long duration. These are just for interactive discussion purposes. If you want to have a very lightweight kind of a use. Okay, so let me just connect to this. I'll share these notebooks of mine with you all. These were prepared for this session itself, so they'll all be shared with you. So don't worry if you're not running this code parallelly with me. You can do it separately also. That's not a problem at all. Okay, so here we can change the runtime, to GPU. Let's see if it's providing me the GPU. Yeah, it's fine. So these are simple the packages that I need for this model to work.
Sir, I want to ask you one question.
Yeah, hello. Yes. Am I audible, sir?
Platform you suggest?
Yes, sir.
Sorry, I couldn't get her voice. What she was saying, it got completely cut. Yeah, please repeat your question.
Sir, you just now told very informative statement that Colab has got limitations, that after 1 day of work with it, it will stop giving you some services. Now,
Yes.
suppose I have a totally different data set, which is not the ready data set, and I am working on some real-time images. In such case, just for 15 or 20 images, it works, and then it stops. So in such case, what is that I should, what will you recommend? That means I should have a good hardware only, or you suggest something different?
Ma'am, look, having a hardware is absolute a privilege, no doubt about that. Having a hardware is definitely a privilege, but
But it
hardware
is
costs
very
a lot.
costly. That's why.
Very costly, yes, ma'am. The laptop that I'm having right now, it's simply a 4 GB NVIDIA card supported laptop, and that too costed me about 75,000. And when I was personally planning to go for an upgrade, it was like looking for numbers like around 1 lakh rupees or more than 1 lakh rupees. So definitely, it's a very big
Yes.
investment. And without, and trust me, without having a proper GPU supported hardware, you cannot run, you can only play with toy problems, simple problems of small size images. That is good enough for learning, for understanding that how model can be built. But for actual solutions, for actual model development, for or giving practical solutions, you will require GPU based solutions. So either, if you have a good internet support, I can recommend you that you go for Collab Pro. If you have slightly to moderate kind of use, because Collab Pro does not guarantee, but yes, it officially says that you will have longer sessions of your longer sessions of your collab. So that means your code can run for longer times with GPU support, and they will provide you better GPU. So Tesla T4, they are saying, and even V100 card, which are the premier line card, they will provide you. Normally they provide K20 or K80 cards when you are having a standard uh, collab interaction. I mean, if I'm getting a GPU right now, it must have been a K80 or I mean, a quadro GPU is being provided to me. So you get a better GPU, you get a better kind of a time session for running your programs, and the cost isn't that much. It's right now $10. It has just, I mean, this year also itself it has been launched for Indian population. Otherwise, it was not for subscription for India was not available. So now it is available. So $10 would roughly, with all those numbers, will roughly count to like about 1,000 rupees per month. So this is a kind of a trade-off that you have to see. Can you have an investment of about 1 lakh in one go? You will have your hardware with you, okay, on the go, anytime, anywhere you can use it, which will not have restrictions on time for you. Or you will go for these online services. Uh, Collab Pro, I find the cheapest. I found the cheapest actually, because others, they have time-based subscriptions. So yes, you will. The first point, you will require hardware. There's no doubt about that. You will require decent hardware, a decent RAM to support your deep learning applications and your deep learning dreams. Actually, without that, it's not possible. And the next cheapest solution that we have is Collab Pro. Nothing else. Even some of my students have gone for this, and they are working on those. Or otherwise, you have some
So
friends in the
one more
academics, or
question I want to ask.
yes.
That if when the training is over and we have a model ready,
Hmm.
at that time, if I want to the code which is there with me, I want to install that after testing and everything is done to some hospital. So in such case, how I should go with that I am not understanding.
Okay, actually, once your model is trained, so
Huh.
you all have to do is download. Is you have to save your model. So Collab, I mean, all these applications, they provide you some mechanism or the other to save your model. Because ultimately, I mean, what do you mean by a trained model? Or do you
Weights
understand by
are
trained model? The weights.
training weights are fixed afterwards after
Yeah,
training is done.
fine. So I mean, if you are using, let's say, MATLAB for training, so ultimately it will give you a model, a trained model in a different file structure. Or if you're talking about Python, or this Collab version, if you're talking about, so then h.h5 kind of file it saves. So you can save your models, and then you can load these models in a different program just to perform the predictions. So you can download, and you can save and download your models. I think I can show you that part today, that how you can download your model. And once you have downloaded this model, so you can load this model into a suitable Python application, and then simply use it for doing predictions rather than training it.
So one more thing, how about using MATLAB rather than this?
Yeah, actually, I personally come from the MATLAB domain. I had done all my research works initially at MATLAB, but then I found myself restricted a lot, because the community for MATLAB isn't that much rich, and the support for Python-based programming is quite high. I mean, it's open source. The codes are available, and I mean, the support is quite very good. And even though, I mean, even if I have the best of the subscription for, I mean, the cost for MATLAB.
Okay, thank you so much, sir. You have solved my difficulty.
Yes, yes. So I would say strongly recommend that you come to Python only. That will be a good way to go.
And the email ID of sir is available anytime. Any of you can contact. Sir,
Yes,
continue.
yes, absolutely, absolutely. Anytime.
Dr. Safraj, continue.
Okay.
Thank you,
So,
sir.
Okay, you're welcome. You're welcome. So we have imported the necessary packages that we require for our program to run. Then you can see the first step. I've just copied the name of the step from my slide only so that you can relate them. So step number 1, loading the dataset. So because this dataset is available in the TensorFlow package itself, so a very simple command like this can help me in downloading this dataset for me. So you can see that the data has been downloaded for me, and now it's there for this program to execute. Now this can tell me the shape of it's my input. So this is 6,000 cross 28 cross 28. So 60,000 samples I have. Each sample of size 28 cross 28. So this is the dimension. So just to see some random. CB2 has not been. Okay, just a second. So this one library was missing. Okay, so just to see some of our random samples, I've just taken some random samples from my data set. So just trying to show that what numbers it's having and what are the labels. So I've just printed the labels also on top of it. So this section has nothing to do with any image processing. This is nothing but just visualizing my data set. So now seeing the shape of my image, I already know my training set is having a shape of 60,000 samples, 28 width, 28 height. Right now, number of channels are not specified. Okay. So now you can see in the next line, it's reshaping my samples. So reshaping to what? A 4-dimensional tuple. Because remember that my convolution operation will require a 4-dimensional option. How many number of I mean, the first thing is the batch size. How many images you're providing at one go? The width of the image, the height of the image, and the channel of the image. In the original dataset, the channel was not provided. So I've just added this channel to it. Now it's so after reshaping, you can see the size has changed, and now the size is 60,000 cross 28 cross 28 cross 1. Now my labels are not of the way that I want. The labels are somewhat different. We can see the labels. I have printed the labels. The labels are 2, 3, 4, 6, 8, 7. I need these labels to be what? Because ultimately, what I want my output layer to have the same number of nodes as my number of labels. So what will happen for each class, I will have one node in the output layer. So I want a 1 from that and zeros from the others. So that means my input, let's say 1, or let's say 0 is my first input. So 0 will be my my output for, let's say, for a class. So 1, and rest all 9 digits will be 0. So 1 0 0 0 0 0 0. For class 1, I will have 0 1, the second bit to be 1, rest all outputs will be 0. So I will have to actually change my my labels from these integer or numeric domains to, or even let's say names at some times, to those okay, it's alignment. So this conversion is actually called encoding, and this type of encoding is called one hot encoding. That means one of the bit is 1, okay, rest all the bits are zeros. So one of the output is hot, rest others are cold. As simple as that. So one hot encoding. I have got 10 classes in MNIST dataset. So I am just putting, depending upon the categories to it, I'm just putting one of them to be of shape of value 1. Rest all other values will be 0. So the shape before one hot encoding was 60,000 samples, but after encoding it, you can see it's now each training output is actually a vector of size 10. If you want to see the output, then sorry, I can add a code to it. I can see y underscore train. Let me just pick up any value. Is this? Same right now. Okay, we'll see to it what happened later on. Okay, so after this, we're building up the model. As I said initially, this is a sequential model. The input shape of my image is 28 cross 28. And then you can see it's having one convolution layer, then we having one pooling layer, then again a convolution layer, then pooling layer. I'm defining the number of filters, 10 filters, each of size 3 cross 3, stride 1 cross 1. Padding is not allowed right now. And this being my first layer, I'll have to define the input shape that it will be getting. So I'm passing this parameter called input underscore shape. The activation function is relu right now. Similarly for this, then I'm just simply flattening out the output of this layer and converting to one dimensional, the addition of dense layer, then again an addition of dense layer. And then I'm just using this summary attribute to print out the summary of my model. And you can over here see the outputs of output shape of each layer, the number of parameters that are being that are over here. So total number of parameters you can see for this model are 27,120. Non-trainable parameters are 0. It's excluding those pooling, the pooling ones. And once I have built my sequential model, a simple one-line command to compile my model. You can see I'm defining the optimizer, the Adam optimizer, metric as accuracy, and loss as categorical cross entropy. And finally, I am fitting my model. That means I'm training my model. I'm defining what will be my X-train, my training data, what will be the labels for it. And then to this, I'm defining the batch size, the epochs, how many epochs I'll be having for this, the validation data, right, for validating the model while it is being trained. Let's run this. Okay, I've not compiled this model. We need to build the model first. This is done. Okay. Oh, sorry, I did not run that part, I guess. Yeah, now it's fine. I did not run this cell because of which I was not getting that output. So now you can see the test part is actually a vector of size 10, and you can see this cell is 1, rest all values are 0. So for I mean, it means that this sample has a target value of, let's say, I think 7. Yeah, 7. It will have a 7. Now I need to build my model. Okay, good to go. So now it's running this line. You can see the first epoch has started. A total of 10 epochs. So let's just give it some time to initialize. I think I am using GPU. Yeah. It even shows how much GPU I'm using. Oh, it started. Good. So you can see this is the loss value, and it is gradually declining. This is the training loss, training accuracy, the validation loss, and the validation accuracy. The loss is on a declining side. The accuracy is on the ascending side. Similarly, I can have a similar trend for the validation also. So validation is actually the unseen data, and the training data is the one that is being fed again and again in each epoch. Let's just give it some time to complete. Okay, so it's now complete. Now I can plot using this history parameter. I can plot the loss values and the accuracy values. This was the loss curve. You can see the validation and the training loss pretty much on the favorable side. Similarly, the accuracy. my model accuracy was around 97%. I can use this remaining code to find out the confusion matrix. I have this predefined class available to draw the confusion matrix. So this is the confusion matrix for me. This is the accuracy 97, and 97.66 is the precision, the recall, and the F1 score are being shown over here. So can I mean, this was the application on the MNIST, on the conventional data set. I also actually selected a data set, and this was a data set of some. Let me show you on my laptop. Okay, so this was the data set I had, leaves data set, and you can see these are the leaves of some of a citrus fruit. So with some problems, this is the black spot problem, and then we have some canker problem, the greening problem. We even have some healthy leaves. So can I do this classification? So for this purpose, I had to upload my data set. Okay, so my data set is already uploaded, and you can see it's here. For this, I made another code, and this one is by the name leaves. Let me just open this one. I can do away with this now. It's very important to close your runtimes. Otherwise, yeah, it's very important to manage those sessions. So I took up almost 0.78 VRAM of the GPU. So I'll terminate my MNIST session to quickly show you the other data. Yeah, so this is for the leaves problem. No, I'm not applying VGG19 here. I'm not even applying Resonate 50. I'm simply making my own custom model. So now you can see the code for taking this data is somewhat different. I have uploaded the data in my lab, in my collab, in my drive. So this is the data available in my drive. You can see I've given the full path: content/drive/my drive /collab notebook. This is the name of my folder. Then then citrus, then leaves. So this is the place where my my data is actually available. I think I'll have to change this name. Yeah, I think now it will be this. And after that, this it will be KIET FDP. The name has to be right. Okay. So these initial codes, they're all about data set. So how you're picking your data set and how you're loading it will all depend upon the source of your data set. So are you picking up from your system or from the from even you have a possibility of attaching Kaggle to your drives. So you can directly load your data set from Kaggles to download your data set from Kaggle to your drive. Because actually, if you download your data set to this collab, so the session, till the point the session is active, only till that point the dataset will be available. The moment session dies, your dataset will be gone. So if you have a large dataset, then every time you'll have to load your dataset. So better you have it on the drive so that it's not lost. Let me see if I can. No, it's not able to find my drive collab notebooks. Just a second. Let me just check the path to it. Okay, let me just rename this. Just a matter of path. I can also see it from here if my path is correct or not. This is the button that I need to press to connect to my. Okay, I need to give the authorization for this. So just copy this code here, press enter, and this is now attached. Yeah, it's mounted now. So So you can see now it's picking up the values. It's now picking up the files actually. So I have files in my data set. Let me show you that. So KIET, citrus, leaves, and it has picked up from healthy. It has picked up 58 files. From black spot, it has picked up 171 files. So this was the code I've written for picking up files from a folder. So it's iterating on each folder and picking up files from it. So 171 files have been picked up from the black spot folder. The black spot folder has 171 files. I know that. So this will take some amount of time, maybe about a minute or two. Okay, I have 11% battery. Just give me a minute. I'll just connect the charger to it. Meanwhile, let us just allow this to complete. Okay, so now it's in the third folder. It has picked up 163 files. And these are big size images, actually. These are not small images. You can see the size of these images. It's almost 50. It's high definition images, 1520 cross 1417. So these are quite good size images. Some of them are small, some of them are, but these are good enough, 256 or 256. So these are good standard sizes. And I'm building a model on 224 cross 224. So these will work quite fine. Okay, so now it's in the fourth folder, greening. Okay, let me just go through this part. I had initially calculated it. So you can see once this part is over, I'll plot these random values. So you can see these are the random images it picks up. This is the black spot image, another black spot image. Then you have some healthy file also. Once this is done, I'm just trying to find out what values are there in my sample. So these images are actually nothing but vector of some numbers. So 248, 242, 240. These are the pixel intensities given in value ranging from 1 to 255. So after this, I'll try to normalize them. So this is the step to normalize these. So once they are normalized, these big numbers, 245, 233, 239, they will all be converted between 0 and 1. So our numbers should always be normalized whenever we are working in model development activities. We should normalize our data sets. Then the labels are actually extracted. They are then again encoded. The step that we have done earlier, performing one hot encoding. So we have prepared our data, then we have prepared our labels, and now is the time. I'm just printing the numerics, nothing else. You can see those big numbers are now converted to between 0 and 1. So decimal values you can also find. So once that is done, now you can see a division into train and test is being applied. So I have prepared my data set. I have downloaded my data set, prepared my data set. Now I'll divide my data set, because this data set is not divided. The MNIST data set was pre-divided. Now this was not divided. So I'll use this function called train test split, in which I provide the complete data set. I provide this list of complete labels, and I define the test size. How much, what portion of test size should I have? So 0.2, 20% of my sample will be tested. Then it will be stratifying the labels. Stratification of, this division will be on the basis of stratification. So stratification means from each class, it will pick up proportionately. So it will not happen that your entire training data set is overloaded with one class and doesn't have any elements from the other class, because this division is random. But that if I leave it completely random, then this kind of problem can happen. So it's better to stratify. Next, you can see a model is being prepared on the similar way as we made the MNIST model. But over here, as the images are not of smaller size. In the MNIST, the images were very simple, 28 cross 28 cross 1, single channel images. Here you have 3 channel images of a bigger size, 224 cross 224. So you can see my number of filters are also on the higher side. So I have one convolution layer of 16 filters with kernel size of 3 cross 3, stride of 1 cross 1, padding same. That means I'm not reducing the size of my feature map. It remains the same as my input image. And then this size is reduced by the pooling layer. Then I have applied normalization. This is regularization, not normalization. This is regularization. Dropout is a layer added to the model to regularize, because at times the model can overfit. It can tend to mug up certain features. So to avoid this behavior of the model, we can apply various regularization techniques, adding dropout layer, adding batch normalization, adding kernel regularization of L1 and L2. So these are those aspects that you need to delve into once you are training your models. So I found while I was training my model initially, I found that the model was overfitting. So I added a couple of dropout layers, very small dropouts. I've added 0.2 and 0.2. This value can range between 0 and 1. Normally kept between values like 0.4, 0.5, but I've kept a very small value. Then simple by after these multiple convolution and pooling, I've simply done what? I've simply done this flattening of this. And after this flattening, I have one layer of 128 nodes, dense layer, other dense layer of 4. Actually, initially, I was running this problem for 4 classes, but now I have 5 classes. So that's why it's 4. Then I'm simply compiling the model, fitting the model. You can see this, the steps are the same. Load the data set, pre-process the data set, divide the data set, build the model, compile the model, and then fit the model. And after the fitting, you can see this model goes up till after 20 epochs and with minimum training. You can see the loss came down to 0.44. The testing loss was quite low of 0.44. The accuracy was 81%. The validation loss was close to it, 0.61, and the accuracy was 0.75. So this was the curve, quite jittery, but still the trend is quite acceptable. The trend is quite there. Similarly, the accuracy trend, you can also see an upward trend in this. Followed by this, I calculated the accuracy of my model by performing predictions on the test data. So it came out to be 75%. Then I calculated the confusion matrix, and you can see the diagonal elements, they are lightened up. The worst of the performance came from the class 4. Why? Because that class is having very less number of samples. You can see a very bad distribution of data set over here. If I show you this, the first set is having 58 samples. The second one is having 171 samples. The next one is having 163. So how much badly this has been, this data set is there. You can see the class imbalance problem is quite evident over here. So the classes which are having higher number of samples, obviously their training was, they were contributing more to the training set. So we try to, either we try to have a data set with moderate class imbalances, or we try to apply some augmentation techniques by which we can handle these class imbalances. So because of which you can clearly see the performance matrix having some dark shades over here, because the samples of the healthy images were only 58, and of the previous one they were almost 213. So you can see the class which had more samples is having a better accuracy. The class which is having a lesser number of samples is having lesser accuracy, because of which this curve is quite jittery. So had I been having a better data set, this model would have worked fine for me. But yes, this was just to show you that we can have how we can work with data sets of our own. So the same way we can take our own data set, put it on the drive, use such a code of those 5 basic steps: loading the data set, pre-processing the data set. And now this pre-processing can be of a varied nature, depends upon your problem that you're talking about. Are you applying augmentation, to what level of scaling you are applying, are you applying are you using image generators or not? Those are another aspect of deep learning model development. So once that is done, you divide your data set, build your model, compile your model, and you fit your model. Simple. Okay, so I think, sir, it's time. I've tried to cover up the goals that I have set initially in my slide. yeah, tried to cover up almost all of them, and I have high hopes that I would have conveyed some of my knowledge to the fellow participants.
Yes,
Uh,
sir.
Over to you.
Okay. Thank you, sir. Thank you. Thank you, sir, for sharing valuable insights about CNN. We hope participants have learned new and evolving concepts of CNN, and this will help them in their research work. Thank you again, sir. Now, sir, would you like to thank sir?
Dr. Sapraj, good morning.
Good morning, sir. Good morning.
And in a small time, means in 2 hours, you have explained excellent way. Uh, Even people like me who were not knowing CNN, I have worked in image processing and computer vision area. And but
Okay.
as my topic is content-based image retrieval in
Oh,
PhD
great,
program,
great,
and
great.
but that time there was no deep learning concept. So
Yes, yes.
I have used local binary pattern and fuzzy c-mean and all. So
Yes.
now I find ki, with the help of CNN and all, results are really very good and nothing
Yes.
to do. Just only take the image and you just put and you will get everything. And
Yes.
even for the segmentations, I have worked very hard to get into the four clusters. And
Yes. Yes.
now it is everything just like go in market and take a food and eat. So I think participants have benefited. If I understood, then I think everyone understood. So thanks, sir.
Okay, sir. Okay. I will share these
Uh,
codes that I've made
Code,
with
yeah,
everyone.
yeah, code and PPT you will mail and
Yes,
us.
absolutely. I'll absolutely.
And we will finally at the last day we will mail to all the participants, so participants should be happy. You will get all the slides, all video recording, but you will get last day because we have to compile and then we have to mail to all of you.
okay.
Okay.
Sir, I have one request. Kindly switch on your camera for once. We'll take a screenshot with you.
Go up to HS now. Just a second.
Okay.
Am I visible now?
Yes, sir.
In the browser mode, actually, in the browser mode, na, this was not allowing me to open my camera as well as perform slide presentation parallelly. So
Okay.
that's why.
No worries,
So
sir. Thank.
I hope that participants would have gained something out of this session, and I would be very much open to your suggestions and as well as your queries. My email ID, sir, will share with you all, and you can write it to me, and I'll definitely try and respond to your queries.
Sir,
And
there is one participant, Anjali Nayak, ma'am.
yes,
Your mic is on. You can speak now.
Sir, sir, your session was really useful. And
uh,
as far as implementation part, uh, yes, I will definitely try all those things that you have told. But meanwhile, my internet was not there, so I couldn't see actually the last part. So I request the organizers to, instead that you share it on the last day, if you share your the videos on the same day, then at
oh,
night we will able to listen nicely. And because afterwards what happens, then you are busy with some other activity. Right now, you are in the tempo, you are listening to the video lectures and attending the FDP. On the same day, if you share the PPT videos, that will be a great thing.
right. So I think this is
Thank you.
ma'am and Dilkeshwar sir can look into.
Yes, sir, sure. Sir, there is one more candidate who wants to talk to you. Shri Lakshmi, ma'am.
Yes, ma'am.
Ma'am, mic is on for you.
Yes, thank you, ma'am. Thank you, sir. The session is so informative. Sir,
Thank you,
my
ma'am.
question is here we started with the random filters with the random set of filters. At the end of the CNN, we are going to get the accurate results based on the sets. Can we say after that? That means we are adopting the filters by all these iterations. But at the end of the CNN, can we say that, can we find out what is the filter is best for our inputs?
Look, all these algorithms, na, these are optimization algorithms that are running in the backend, and they do not guarantee the best. Okay,
Okay.
the gradient descent algorithm that is working at the backside, that as algorithm does not guarantee the best for every problem, but yes, a very close local minima is there. So a very close approximation you will get, definitely. I hope you know about this approximation property. So all these neural networks and all these, I mean, specifically if I talk about neural networks, they're approximators. So they're approximators to the best. Okay, so they will definitely guide you. The algorithm of this adaptation will definitely guide you to a very close local minima or a very close possibility to being the best. But it does not guarantee the best. That is always there. So even because that is a fact where I mean, how do we know that for how much epochs should we run? And does this I mean, does this number of epochs of training our model, does it guarantee the best model? No, it does not. So that guarantee will never be there, ma'am. It will always be a close approximation. But look at the, I mean, look at the problem that has changed. Earlier, I was trying to do all those extractions. Now, you also yourself think about, if let's say I have got 100 features to extract, let's say 100 features. How do I know that I have extracted the best features? Or how do I know I've selected the best possible features? There's always a chance of missing out something, even when we were doing things manually. So that point I mean comes here also, that we are doing a very close approximation to the best possible. However, we still don't know the best for our problem. If our problem is very trivial enough, we may find the best. But if our problem is not trivial enough, which most of the real world problems are, so in that very case we will be doing an approximation of the best. We will be close to the best, but not does not guarantee the best. Even though we train for 100 epochs or 200 epochs or more than that, it does not guarantee. So we try to compromise with something, because ultimately a very big load of ours has been taken on by the system.
Sir, I have one more question. Thank you, sir. It's, sir, here
Yes, yes,
in
please go ahead
CNN,
with the question.
generally we'll use the convolution plus pooling layer for the feature extraction and the minimization of size, right? So instead of these combination for the feature extraction, can we add at the end we'll use the CNN fully connected layer that is common for all. Instead of convolution and pooling combination, can we use any other AlexNet or efficient net like that for
Yes,
the
yes,
feature
yes, yes,
extraction?
yes. You can use. That's, I think, the next session of yours will be talking about transfer learning, and there you will understand that for complex problems, training our model from the scratch is going to be kind of a problematic scenario, because right from absolute, because training from the scratch means absolute random values, no features whatsoever you know about. So you are trying to find out a needle in the haystack. So other people have done trained their models to a certain extent, to a certain number of problems. So VGGNet or some other network has been trained to some extent. So you can take those models to your problem. You can take those weights also to your problems, and then you can start training from that point onwards, rather than training right from the scratch. So if you don't know about the architecture, the problem is complex, you can take the architecture, existing architecture, maybe VGG 16, VGG 19, maybe ResNet. So those architectures are available for you, and then you can apply transfer learning to it. That means some weights, I mean some problems that have already been trained for, some weights you already have, you can take those weights and apply them to your problem, and then start training from that point onwards, rather than training from the scratch. So that will be done. That should be I mean that is mostly is being tried by people in computer vision. That's because that saves a lot of computation power and time also. So if that is a way out for you for your problem, you should definitely apply that. And I think the upcoming sessions are going to talk about that.
Okay, sir. Sir, I have one more doubt. It's
Yes, ma'am.
by using of convolution layer, we are going to extract the features. Am I right?
Yes, ma'am.
Yeah. For that, for example, if I am giving the one image, for example, our diabetic retinopathy image, it's
Okay.
based on the features of that particular image. It is going to extract the some of the features. But
Yes.
I thought it's one feature is missing with this convolution. Can I specify externally to specify these features are very important to extraction?
There are some ways of applying. I mean, some attention based mechanisms have been proposed recently that you can explore, which try to focus on certain specific features of our model. Okay, but again, that is again controlled by the algorithm itself. But you can focus on certain features more as compared to others. So there are certain some recent research on attention mechanism involvements in training of a model. So I believe you're trying to ask questions something related to that. Otherwise, specifically telling the model that you focus more on that feature, that is a bit difficult thing, because how do you know that that feature is important? If you already have that much amount of information about the system, then your kernel shapes can be of a different types. You can mold your system. But if you don't have much idea about your data set, or let's say you don't have much idea about what aspect, because variability of features in the images can be high. So in that case, you will have to go for a random exploration. But you can make the most of the recent research in attention based mechanisms.
Okay, sir. Thank you, sir.
Okay.